Hi everyone, welcome back. In today's session, we are continuing with part 3 of our series, Write PySpark Joins like a Pro. If you have been following along, in part 1, we have explored join types in PySpark. Then in part 2, we have looked at how to write join conditions for different scenarios, single column joins, multi-column joins, multi-table joins, and more. Now in part 3, we are going a step further. We will look at some common pitfalls that often people run into while writing joins. Along the way, we will pick up some practical insights on writing joins. Just like the previous parts, even this one is a guided walkthrough of working examples in a Databricks notebook. So before we dive into the demos, let us take a quick look at what is included in this session. There are two main sections in the Databricks notebook. Section 1, Common Pitfalls. Section 2, Practical Insights. In Common Pitfalls section, I have covered 6 different scenarios. First, we will look at what happens when you apply filters as part of a left outer join and why there is a right way and a wrong way to do it. Second, we will talk about how to dedupe data before joining. I will show you 3 different approaches and walk through their pros and cons. 3. A quick but important reminder. Filters in PySpark are case sensitive and that can sometimes lead to unexpected results. 4. We will discuss how to handle nulls in join conditions and what to be careful about. Fifth, we will dive into how to deal with many-to-many relationships when joining data frames. Finally, we will visit the broadcast join. We will look at an example, when to use it, and also when not to use it. In Practical Insights section, I will share some of my thoughts and examples that go beyond the basics. For instance, we will see how a given join scenario could be written in multiple ways. We will also look at joining tables on a range of values with a clear example. Lastly, we will touch on role-playing dimensions, something you often see in data warehouse dimension modeling, and we will see how to handle them in PySpark joins. So as you can see, there is a lot of good stuff packed into this session. Let us get started and dive right into it. Actually, before we dive into the main sections, let us quickly set the stage. In terms of structure of presentation, for each scenario, I will first walk you through a simple illustration on the slide to help visualize the concept. Then we will switch over to the Databricks notebook and explore the corresponding PySpark code, followed by key takeaway for that scenario. This pattern repeats for each of the 9 sections in this session. Slide first, then code walkthrough, followed by key takeaways. Sounds good? By the way, there is one other thing that I want to show you before we start diving in. This is the Databricks notebook that we will walk through shortly. For now, I just want to point you to a couple of things. Firstly, the entity relationship diagram for the TPCH database. Some of the examples in this session rely on the tables in a TPCH database. Secondly, example data. This is where I am populating the example data. As you can see in the table of contents, there are 6 different data sets that I am populating for the demos in this session. All right, with that groundwork in place, let us begin with common pitfalls scenarios. In the common pitfalls section, we have 6 scenarios to go through. So let us move on to the details. The scenario we have got here is that we have 2 tables, customer table, orders table. Say we want to write a query in such a way that the output contains all the rows from the customer table along with only those records from the orders table that have an order date on or after a certain date. For this, how will you go about writing a query? Obviously, that will be a left outer join with customer being the left table and orders being the right table. But one thing to note here is that the data filter that we want to apply is on the right table. This will make writing this left outer join a little bit tricky. For writing the query itself, one might be thinking of writing it in 2 different ways. Option 1, first filter the orders data and then join it with customers data. Option 2, first join the 2 tables and then apply the filter. But between the 2 options, which one will give us the correct results? Let us first take a look at the illustrations for option 1 and option 2. Then look at the code to see as to which of the 2 options will give us the correct result. Conceptually, this is how option 1 will look like. In option 1, step 1 is to filter the orders table based on that filter criteria so that we get these filtered orders. Then in step 2, we do a left outer join between the customer table and the filtered orders. So in the output, we get to see all the customers along with only those orders that satisfied our filter criteria. So this conceptual diagram suggests to me that going by this approach, we will get the results correctly. Then what about option 2? In option 2, the first step is to join the 2 tables, customer table and orders table. Then apply the filter. The thing is that because we are applying the filter on the combined data set of customers and orders, the effect of filter will be seen across both the tables. Even though the filter we have is on the orders table, which would filters the orders data, but the effect of that filter would also be seen across in the customers table as well. So from the customers table, only those customers will be picked up who had a matching filtered orders data. This would mean that in the final output, going by this option, it will not contain all the customers' records as we expected. That means the output that will be generated going by this option will be incorrect. Having said that, let us validate our theory by running the code. Now, let us look at the code for option 1 and 2. In option 1, the approach is to filter the orders data first and then join it with customer data. Let us see how this has been implemented. Here we are joining the customer data frame with the orders data frame, and those two data frames are being joined on the customer key. Apart from specifying the join condition, here we are also specifying the data filter. What this data filter is doing is filtering this orders data frame on this filter criteria. And the thing is, because we are specifying this filter criteria along with the join condition itself, the net result of it is that the orders data frame will be filtered first, and it is that filtered data that will be used to join with customer data frame. And given that the join between the two data frames is left outer join, in the output you would see all the customer records, along with it only those order records that satisfied this filter criteria. I hope it makes sense. Now let us run the query and see how the output is like. The output count is 750,000. Knowing the count of records in the customer table, I can confirm that the output returned by this option 1 is correct. Now let us go on to see the output from the option 2. In option 2, the approach is to first join the two data frames and then filter it. So going by that approach, here we are joining the two data frames and simply specifying the join condition as the customer key, join on the customer key. And here we are not filtering the data as in option 1 because I simply commented this line out. Instead, after joining these two data frames, only then we are applying this data filter. Let us run this query and see what happens. It returned us 6,000 rows, which is far below the expected record count of 750,000 rows. So this confirms to us that the option 2 will return us incorrect result, whereas option 1 will return the correct result. Here is what I want you to take away. If you are writing a left outer join and a filter needs to be specified on the data in the right data frame rather than on the left data frame, make sure that this filter condition is specified along with the join condition itself rather than applying this filter after the two data frames are joined. Because if you specify this filter along with the join condition itself, in such a scenario, the data in the right data frame will be filtered first before joining it with the left data frame. Now that we have seen how a left outer join can trip us up, let us look at another common one that you might run into. For deduping data frames before a join, the high level value of the scenarios is that, say we want to join two data frames. However, one of the data frames has been found out to be having duplicate records. In such a scenario, how do we eliminate the duplicates before joining the data frames? Even before going into the details of this scenario, I want us to have a good understanding of the types of duplicate data itself. Broadly, there are two types of duplicate data: exact duplicates and duplicates on business key. And I have put together a couple of slides to help us understand what each of these duplicate data types are. So let us have a look at them first. Exact duplicates is one of the two types of duplicate data that we normally come across. But what does exact duplicates really mean? When two or more rows have identical values across all the columns, they can be referred to as exact duplicates. For example, here we have three rows of data, and if you look at the values in each column, they are exactly the same between the rows. Such duplicate data can be referred to as exact duplicates. Then what is the solution for exact duplicates? Solution is very simple. Simply pick any one of the duplicates as the solution. For example, here, out of those three rows, simply pick one of those three rows as a solution for deduping these exact duplicates. It is that simple. Next, let us see the next duplicate data type, which is duplicates on business keys. To understand the meaning of the second type of duplicates, which is duplicates on business key, let us look at some example data. In this example data, the business key was defined on two columns together, which is invoice key and supplier key. And the business key is meant to be uniquely identifying rows in a given data set. But as you can see here, these business keys are duplicate. At the same time, if you look at the values in other columns, for example, invoice amount, the values are different between the rows. Similarly, in the last updated column, the values are different between the rows. So, in this scenario, wherein we have duplicates only on the business key and not necessarily on other columns, we can refer to that duplicate data as duplicates on business key. And from a solution perspective, there are two different approaches that we could adopt. One is to pick any one of the duplicates as a solution, and the other option is to pick one of the duplicates based on a tiebreaker column. But which of the two solutions to go with, it all depends on what is acceptable to the business users. Next, let us take a closer look at each of these two solution options. When a given data set was considered to be duplicates based on the business keys, then one of the approaches to remove duplicates is to just pick one of the duplicates. For example, here we have three sets of duplicates based on the business keys. Following this approach, when we dedupe this data, what will happen is for each set of duplicates, one row each will be returned. For example, for this first set of duplicates, we have three rows, and as part of deduping, one of these three rows will be returned. Similarly, for the second set of duplicates and third set of duplicates, one row each will be returned. That way, at the end of the deduping, it would return three rows for these three business keys. But the thing is that in this approach, we are deduping based on the business keys only. As a consequence, limitation of this approach is that there is no guarantee that the same row will be returned every time we dedupe, even if the underlying data hasn't changed. Each time you run it, it could return a different row for each of these business keys. For example, for this first set of data, first time around, it may have returned us this row which has this invoice amount as $100. The same data and the same business key, second time around, it may have returned as $120. In other words, in this approach, for each business key, different row could be written at different times. That is the limitation of this approach. Is such variation in the output acceptable to the business? If it is acceptable to the business users, we can proceed with this approach. But what if this approach is not acceptable to the business users? Instead, they want consistent results by returning the same records every time we dedupe. This is where the second approach comes into picture, which we will discuss next. This approach is an extension to the previous approach. In the previous approach, we were deduping based on the business keys only. And the limitation was that there was no guarantee that we get the same results every time we dedupe. Whereas in this approach, we will dedupe not only based on the business keys, but also by considering additional columns. Say for each business key, we wanted to pick up the latest of the duplicate records based on the last updated timestamp column. So for the first set of duplicates, of the three duplicate rows, the latest of them is this one. Similarly, for the second set of duplicates, this is the latest row. And for the third one, this is the latest record. That way, as long as the underlying data hasn't changed, the latest record for each of the business keys wouldn't change either. What it means is every time we rerun deduping, it should and would return the same results consistently. Does that make sense so far? In terms of implementing this solution, there are 4 steps. Step 1 is to partition the data frame based on the business key. Here we have 3 unique business keys, 3 distinct business keys. So in terms of logical partitions, there would be 3 logical partitions here. Then step 2 is to sort the data within each logical partition, either in the ascending order or descending order, depending upon the business requirements. Then step 3 is to assign the row numbers within each partition. For our example, let us pretend that we have sorted the data in the descending order so that the latest of the records will be assigned row number 1 and second latest would be assigned row number 2 and then the oldest will be assigned row number 3 and repeat this process for second set of duplicates and third set of duplicates. In the second set of duplicates, the latest record assign the row number as 1 and the second latest as 2. Similarly for the third one, latest record row number 1 and then the second latest row number 2. And in step 4, pick up the first rows or the rows that were assigned row number 1, pick up those rows. This one, and this one. Obviously, these rows that had this row number as 1 are the latest rows for each of those business keys. The end result is the output contains 3 rows that were the latest records from each of the 3 business keys. The main benefit of this approach is rerun the deduping process any number of times, the returned result wouldn't change. unless the underlying data changed. I hope that is clear up to this point. Having discussed the three different scenarios for duplicate data, let us recap quickly. A quick recap on the types of duplicate data and the solutions for the same. There are two types of duplicate data: exact duplicates and duplicates on business keys. Exact duplicates are duplicate data where two or more rows have identical values across all columns. The solution to remove exact duplicates is to simply pick one of the duplicates. Whereas for duplicates on business keys, we can take two different approaches. Either we may want to pick any one of the duplicates or pick a specific duplicate record based on not only the business key but also based on additional tiebreaker columns such as last updated column, etc. With that theoretical understanding in mind, next let us look at the example code for the same. For exact duplicates scenario, this is the example data. In this example data, we have three sets of duplicates. First three rows is the first set of duplicates, and then the next two rows is the second set of duplicates, and the last two rows is the third set of duplicates. And for each set of duplicates, as you can see, the values across each of the columns are identical. Then, when it comes to deduping this data, our expectation is that for each set of uh, duplicate rows, in the output, we just expect one row. That way, for these three sets of duplicate rows, in the output, we expect just three rows out of these nine rows, seven rows out of these seven rows. Now let us take a look at the code to see how the code was implemented. Here you can see that the invoice exact duplicates data frame, which has those duplicate data as we just looking at. And on this data frame, drop duplicates method is being called. That's all we will have to do for removing the exact duplicates from a given data frame before joining it with other data frames. Now let us run this code and see what happens. In the output, as expected, we have three rows. For the first set of duplicate rows, there was one row returned. Similarly, for the second set of duplicate rows and for the third set of duplicate rows, one row each was returned in the output, which was as expected. That is about the exact duplicates. For data that is duplicates on business key, as indicated earlier, we have two different approaches. The first approach is to just pick any one of the duplicates for each of those duplicate business keys. For this example, the example data looks like this. Similar to the previous scenario, here also we have three sets of duplicates. And the thing is, for each set of duplicates, if you look at the values in the columns, those values are not exactly same across the columns. It is different. So for this reason, we are calling this example data as the duplicates on business key. And when we dedupe this data, the expectation is that there shall be three rows in the output with one row each for each of the business keys. Now let us look at the code to see how this deduping logic was implemented, especially for this particular scenario. So in the code here, we have the data frame, invoice data frame, which has the duplicate data based on the business keys. And on this data frame, we are calling the drop duplicates method, which is the same as what we did in case of exact duplicates as well. However, the difference here is that while calling this drop duplicates method on the data frame, we are also passing the business key as well. So drop duplicates method along with the business key tells the program that we want to dedupe this data based on the business keys. Otherwise, rest of the procedure is the same. Like after deduping the data on the data frame, you just join it with other data frames and then so on. Now, let us run the query and see what happens. As expected, in the output, we have three rows, one row each for each of the duplicates, each of the duplicate business keys. But the thing is that, for example, for the first row, in the input, we have three duplicate rows. But in the output, going by this approach, which of those three rows will be picked up? There is no guarantee. And each time you run this program, it could be returning as a different row as part of the deduplication. In this particular example, because we have a very small data set, it is returning the same row every time, but there is no such guarantee with larger data sets. So this is the limitation of this particular deduping approach. If that makes sense, let's keep going. Coming to the second approach, in this approach, we want to dedupe data not only based on the business keys, but also by considering additional tiebreaker columns. The example data that you see here is exactly same as what we had seen in the previous approach one. In this particular approach, in the second approach, for each of the duplicate rows, for each set of business keys, we want to pick the latest row, going by the last updated date. That way, for this first set of duplicates, this is the latest row. And this latest row has this invoice amount as $150. Whereas for the second set of business keys, this one is the latest row where the invoice amount is $55. Similarly, for the third set of duplicates, this is the duplicate row with invoice amount as $275. And in terms of implementing the solution, we have four steps for this particular approach. And now let us see how these four steps have been implemented in the code. Here in the code, we have this invoice data frame that has duplicates on the business key. And the first step we are doing is to partition the data frame based on the business keys. That is the step number one. And then step number two is to sort the data within each partition based on the last updated column. And in this case, the sorting is done in the descending order because from among those duplicates, we wanted to pick up the latest of the rows, not the earliest of the rows. So depending on the business requirement, you may want to do either descending order or ascending order. But in this example, we are just sorting the data within each partition based on the last updated date in the descending order. That is step number two. And then step number three is to assign the row numbers within each partition. Given that we were sorting the data on the last updated date in the descending order, the earliest of the rows, the latest of the rows will get the row number one, and the second latest would be getting the row number two, and so on. Then step number four is to Pick the first row from within each set of duplicates. So step number one is to partition the data frame based on the business keys. Step number two is to sort the data based on those tiebreaker columns. And then step number three is to assign row numbers within each partition and then pick the first rows from within each partition. Now, let us run this query and see what happens. As expected, we received in the output, we got three rows, one each for each of those business keys. And also, one thing to note here is that, as expected, for each of the business keys, we have got the latest of those duplicate rows. This was the latest duplicate row for the first set of business keys, wherein the invoice amount was $150. Similarly, for the second and third set of duplicates, we got the latest latest of the duplicate rows. That is about the second approach to deduping the duplicates on business key. Duplicate data can be one of two types: exact duplicates, duplicates on business key. In case of exact duplicates, we can pick any one of the duplicates as part of deduping. Further, we can use drop duplicates method of the data frame. Whereas, in case of duplicates on business key, we got two options. Option one, pick any one of the duplicate rows. For this, we can use drop duplicates method of the data frame, but this time passing it the business key as parameter. However, this method has a limitation. The result might be non-deterministic, meaning every time you do, it might return a different result. Option 2, dedupe based on business key and sort the duplicates on tiebreaker columns in ascending or descending order as appropriate. With this option, the output will be deterministic. That is, the same result will be returned every time each you do, as long as the underlying data hasn't changed. Which of these two options to use for deduping on business key? It all depends on what is acceptable to the business users. All right, that was pitfall number two. And here is another one that often sneaks into PySpark join logic. Data matching in PySpark is case sensitive. Unless we are aware of this fact, it can sometimes lead to unexpected results. So I have put together two scenarios just to demonstrate this pitfall. In scenario one, we want to do an inner join between employee table and department table on department ID column. The question I have here is that when we do the inner join between these two tables, how many rows would be returned? To answer this question, let us take a closer look at the values in the joining column. For the first row in the employee table, the department ID is DPT501, which is all uppercase. And for that, we could find a match in the department table, which is DPT501, which is also all uppercase. So this row would be returned by the inner join. Then for the second row, we have this DPT502, and for this, we could find an exact match, including case. So this row will also be included in the inner join output. Then third row, we will come back to it in a moment. Let us go on to see the fourth row. Here for the fourth row, we have this department ID 503, and for that, we could find a match, including the case. So this row will also be included in the inner joins output. Then coming back to the third row, this third row has this department ID DPT502, wherein the prefix is all mixed case. For this, if we were to look at the department table, in the department table, we could see only the DPT502, which is all uppercase. So for this particular row in the employee table, for this department ID value, it couldn't find an exact match, including case in the department table. So this row wouldn't be included in the inner joins output. In other words, the inner join for this data scenario would return just 3 rows and not all the 4 rows. So the point I want to highlight here is that table joins in PySpark are case sensitive. Having seen that, let us look at another scenario that could also be affected by case sensitivity. For scenario 2, what we have got here is that we are joining 2 data frames. Apart from joining the data frames, we also wanted to specify a filter. Here, as highlighted, the filter specified is Japan, which is all in uppercase. So for this filter, it would return the results, it would return the data. Whereas if I specified the filter in mixed case, it wouldn't return any data. The reason being, in the underlying table, for this column, all the values were in uppercase. Otherwise, the point I want to demonstrate here is that the string literals that we specify as part of filters are also case sensitive. Now that we have seen the concepts for scenario 1 and scenario 2 visually, let us jump into the code to see it in action. Let us see the effect of case sensitivity on table joins first. Here we have employee data frame and department data frame. As seen in the illustrations, we want to do an inner join between these 2 data frames. The expectation is that the output would contain only 3 of these 4 employees because one of the employees has a department ID, and this particular department ID, for this we couldn't find an exact match in the department table due to case sensitivity reasons. Let us confirm this by running the query. Here in the query, as you can see, we are joining the employee data frame with the department data frame and joining it on the department ID and doing an inner join. Let us run the query and see how many rows are returned. It has returned 3 rows as expected. So it confirms to us that the case sensitivity has effect on column joins. Having confirmed it, let us move on to the second scenario wherein we want to see the effect of case sensitivity on filters. In this example scenario, as seen in the illustrations, we are joining the 2 data frames, and additionally, we are also including a filter. In this filter, currently the filter value is all in uppercase. So with this filter as is, let us run the query. So yeah, it did return some data for us with this filter, which is all in uppercase. Now let us change the filter from uppercase to mixed case and see what happens. It didn't return any rows. because because the reason for it is that in the underlying table in this column all the values were in uppercase. So that confirms to us that the case sensitivity does matter even in case of filters. In other words, these two examples confirm to us that case sensitivity affects table joins as well as filters. If you are writing a table join on columns which are of string data type, or if you are specifying a filter in your query and that filter is a string literal, in either case, do remember that data matching is case sensitive. And sometimes this can lead to unexpected results due to the case sensitivity. So that is about the case sensitivity in data matching. Now let us move on to the next pitfall and see how it plays out. To handle nulls in joins, let us start with some background info on nulls itself. A null value in data represents the absence of value. It means the value is unknown. In PySpark, the default behavior of null is like this. When you compare a null with another null, it returns null. Similarly, when a null is compared with a not null value, even in that case, it returns null. That is the default behavior of nulls. However, this default behavior can be modified. For that, we can use PySpark function equal null safe. We will see this function in action in a few moments. For now, let us understand the changes in behavior that this equal null safe function can bring in. In the changed behavior, when you compare a null with another null, true is returned. Whereas when a null is compared with a not null value, in that case, it returns false. With this background info in mind, let us look at different scenarios for handling nulls in joins. This is the first of the three scenarios for handling nulls in joins. For each scenario, we will go through the illustration first, then we will walk through the related code in the notebook. The scenario here is that we have orders data frame and line items data frame, and we wanted to do an inner join between the two data frames on order ID. But the thing is that, as you can see here in the orders column on which we want to do the join, there are some nulls. However, we don't want to modify the default behavior of nulls for this particular join scenario. In such a case, how will the output of this inner join be looking like? I will pause here for a moment in case you want to take a guess. All right, as mentioned earlier, when we join a null with another null, it returns null. The effect of it is that such rows would be dropped out of the output. So that way, these three rows will be dropped out of the output because these three rows are trying to join null in one table with null in another table. Before we look at the code for this, let us note the customer ID for this order where the order ID is null. The customer ID for this is C101. The expectation is that these three records for which we were trying to join on the null should be excluded from the output. Let us see in the code if our expectation is correct. For scenario one, we have already seen the example data in the illustration itself. So let us go on straight to the code. In the code, there is nothing special about it. All we are doing is joining the orders data frame with the line item data frame on order ID, and we are doing an inner join. The expectation from this query is that those records in the input where they have nulls in the joining columns, they should be excluded from the output. Let us run the query and see how the output is. Here in the output, as expected, the customer ID C101 hasn't got any rows wherein the order ID was null. That means our expectation was correct. That is scenario one. Now let us go on to see scenario two. In the previous scenario, we didn't want to change the default behavior of nulls. Whereas for this scenario, let us change the default behavior. For this, in PySpark, we can use equal null save function. Just a quick reminder about this function. When we modify the default behavior and when we want to compare a null with another null, true is returned. The Boolean value true is returned. So what must be happening is that Spark must be assigning some sort of unknown value to each of these nulls. Maybe yes, some unknown value. We don't know exactly as to what unknown value would that be, but for our discussion's sake, let us just write it as unknown. What this would mean is that this record, which has this null here, would be joined to this record and to this record where here it is null, similarly to this record. So in the output, this time around, we should see three additional records for customer C101 where the order ID is null. Let us validate our theory on this in the code. For scenario 2, there is no change in the example data. However, we are changing the default behavior of nulls. For that, we are going to be using the equal null save function. Let us see how that function is implemented in the code. As usual, we are joining the orders data frame with a line item data frame, and then we are specifying the join condition. And it is this join condition where we will have an opportunity to change the default behavior of nulls. For example, here in the commented line of code, you can see how the default behavior was enabled. To enable the default behavior, all we have to do is join the two data frames using the double equal to operator. Whereas to modify the default behavior, we have to write the join condition slightly differently. The difference is that in this case, on the first data frame, on that column that we want to join on, you invoke the equal null save function. And to that function is where you pass the column from the second data frame. That is the main difference. I hope it makes sense. Now, let us run the query and see what happens. In the output, as you can see, this customer ID C101 has three additional records which have this order ID as null. So in the output, we got the output as expected by the changed behavior of the nulls. Whereas If we had not changed the default behavior, then we could not have seen these three additional records in the output. Does that mean should we always change the default behavior of nulls so as to be able to see the records that have nulls in the joins? It depends. As you will see in the next scenario, which is scenario number 3, you may or may not always want to change the default behavior of nulls. To find out more about it, let us go on to scenario number 3. In this scenario also, we will continue with the changed behavior of nulls. However, the example data is slightly different. The difference is that we will use the version 2 of the orders table. As you can see here, in the new version, we have inserted a new order record, and this order record has null in the join column. That means, unlike in the previous scenario, in this scenario, we will have two order records that have nulls in the join column. And given that we are changing the default behavior, even in this scenario, these two records will get joined to the same three records in the line items table. That is, this first of these two records that had null in the join column, this will get joined to these three records in the line item table. Similarly, the second of these order records that has null as well, that will also get joined to the same three items in the line item table. That means we end up getting 6 additional records in the output table. 3 for the customer ID C101 and another 3 for the customer ID C103. This will also mean the same 3 line items are getting assigned to 2 different customers, which is incorrect. We cannot assign the same 3 line items to 2 different customers. So this is the potential risk you take when changing the default behavior of nulls in joins. That is, in some scenarios, we get the results correctly, and in the other scenarios, the results can be incorrect. Having said that, let us validate our understanding by running the code itself. For scenario 3, we have already seen the example data in the illustrations itself, and there is no change in the code. It is the same as the previous scenario. Like in the previous scenario, we are changing the default behavior for nulls. So let us run the code and check the results. As expected for this scenario, we have 6 additional records. 3 records for the customer ID C101 that had an order ID of null. Similarly, for customer C103, we have 3 additional records which have this order ID as null. As mentioned earlier, the problem here is that the same 3 line items are getting assigned to 2 different customers, which isn't correct. So the main point here is that when we change the default behavior of nulls in a join, the correctness of output depends on the scenario. In some scenarios, the results can be correct, but in other scenarios, it can be incorrect. So if you want to change the default behavior of nulls in a join, change it with care. Overall, here is what I want you to take away. To minimize the impact of nulls in a join, ideally do not allow nulls in key columns because, as you may already know, key columns are the ones that are commonly used to join the data frames. If nulls are being allowed in the key columns for whatsoever reason, do have data quality checks in place. Lastly, if you are writing a query to join two data frames, and as part of that query, if you are changing the default behavior of nulls on the joins, then make sure that out of the two data frames that you are joining, one data frame has no more than one null value on the joining columns. Otherwise, expect incorrect results. Now that we know the impact of nulls on joins, let's find out about the next pitfall. You may be thinking that many-to-many relationship is a data modeling issue, and why should I be worried about it? I agree, but what I think is, as a developer writing code to join tables, it is good to know what a many-to-many relationship is. That way, when writing a join for such scenarios, we could have a better understanding. So let us start by understanding what a many-to-many relationship is. Let us take a classic example of student and subject. As you can see in the illustration, one student may study many subjects and one subject may be taken up by many students. In other words, student entity and subject entity, they are in a many-to-many relationship. The problem here is that relational databases cannot directly represent many-to-many relationships. They only allow one-to-many relationship or one-to-one relationship between any two tables. In that case, how to resolve the many-to-many relationships? A typical solution for many-to-many relationship is to have a bridge table between the two data frames. Once we have a bridge table, the many-to-many relationship transforms into two one-to-many relationships. That is, the relationship between the student and bridge table becomes one-to-many. Similarly, the relationship between subject and the bridge becomes another one-to-many relationship. For example, if we look at the student ID 101, it is present in student table only once. Whereas in the bridge table, the same student ID 101 is associated with multiple subjects. That way, the relationship between student and bridge is one-to-many. Similarly, if we look at the subject table, let us pick a subject ID 502. In subject table, this ID is present only once. But in the bridge table, the same subject ID 502 is associated with student ID 101 and is also associated with student ID 102 and then with student ID 103. That means the relationship between bridge subject table and bridge table is again one-to-many. Once we resolve a many-to-many relationship using a bridge table, writing the code to join the data frames becomes straightforward. So let us take a look at the code to see how it was implemented. As mentioned just then, once a many-to-many relationship is resolved using a bridge table, then writing the code for joining the data frames is pretty straightforward. As we have seen in the illustrations, there the student and subject table, they were in many-to-many relationship, and that was resolved by also introducing a bridge table between the student table and subject table. So that's how we see here three data frames, one for student, one for subject, and another one for the bridge table itself. And let us see how the join between these three tables is done here. Here we are joining the bridge table. Sorry, we joining the student table with the bridge table, and then we are joining the subject table with the bridge table. It is that simple. So the key takeaway from this part is many to many relationships is a data modeling issue. Having said that, it is possible to resolve that many to many relationship, and for that one approach is to introduce a bridge table between them. That way, a many to many relationship can be transformed into two one to many relationships. Once we resolve that issue, then writing the joins between them is no different to joining three different tables. That was about many to many relationships. Now, let us turn to the next pitfall. If you are wondering about why broadcast join was included in the pitfall section of this blog, here is my explanation. When writing a broadcast join, I want us to be mindful of the size of the data frame that we want to broadcast. By default, the size of the data frame that can be broadcast is 10 MB. However, we may want to adjust this threshold to broadcast even larger tables. Having said that, if the data frame that you want to broadcast, if it is not small enough as you intended it to be, it could result in out of memory errors. For this reason, I included the broadcast join in pitfalls section. The scenario that is included in here is a simple broadcast join. Otherwise, it doesn't demonstrate any out of memory issues in using broadcast joins. The scenario itself is like this. Join customer data frame, which has 750,000 rows, with nation data frame, which has only 25 rows. So let us hop over to the notebook to see the broadcast join in action. Writing the code for broadcast joins is easy and straightforward. And here is an example. In this example, we are joining the customer data frame, which has 750,000 rows, with a small nation data frame, which has only 25 rows. And because the nation data frame is very, very small, for that reason, we are broadcasting the smaller data frame as part of this join. So writing the broadcast join is that simple. However, if the size of the data frame that we want to broadcast, if it happens to be large, then it could lead to out of memory issues. For that reason, use broadcast join with care. And here is what I want you to take away. Writing a broadcast join is easy. However, we need to make sure that the data frame that we want to broadcast is small. Otherwise, we could run into out of memory errors. So use broadcast join with care. That wraps up the pitfalls. Coming up, three practical insights to help you write PySpark joins like a pro. In the practical insights section, I have included three scenarios. Here, some good news is that the scenarios in the practical insights section are not as lengthy as the ones that we had seen in the common pitfalls section. So let us begin exploring this section. When you are writing a complex query to retrieve data from a database, there is often more than one way to get the job done. Sometimes 4 or 5 different ways, in fact. The example in here is meant to illustrate that point and also to share a few thoughts on how to approach such situations effectively. The scenario we have got here is that we have two tables, service provider and invoice tables. Utilizing these tables, we want to get a list of only those service providers that have at least one invoice, and the payment status of such invoices must be paid. In doing so, one important point to note is that in the final output, we are interested in service provider details only and not interested in the invoice details in the final output. So the query for this can be written in at least 4 different ways. So for this scenario, let us see those 4 different ways of writing the queries in the notebook. As indicated earlier, this query can be written at least in 4 different methods. Using a left semi-join or is-in method, or using an inner join or left outer joins. I won't dive into all the details, but let me point out a few things that really matter. In the left semi-join approach, as you can see, we are joining the service provider data frame with the invoice data frame. While doing so, on the invoice data frame itself, we are filtering the invoice records based on the payment status. So obviously, it would be using only those invoices that satisfies this invoice payment status criteria to do the left semi-join with the service provider. So this is one approach. We can run this query. It returns 2 rows, 2 service provider records. Similarly, in the second approach, wherein we use the is-in method on the data frame. Here, the first step we are doing is get the list of service provider IDs who have the invoice, at least one invoice that has a payment status of paid. So this step gives us the list of service provider IDs that satisfies the criteria. And then on the service provider data frame itself, we apply that filter using is-in method of the data frame. That is the second approach. Even in this approach, we get the same results as in left semi approach. Similar is the case with inner join. And the fourth approach is to join the two data frames using left outer join, but at the same time filter out the unmatched rows. What it means is that here, unlike here we join this service provider data frame with the invoice data frame, and we do a left outer join on this. But as you know, the left outer join would return all the rows from the left data frame along with matched details from the right data frame. Whereas for our requirement, we want only the matched records. So that way, on top of doing a left outer join between the two, we need to filter out the service provider records that couldn't find a match in the filtered invoice data. So that is where we apply this is not null function on top of the left outer join result. So all these different approaches give the correct answer. In such a case, which one of these 4 solutions to go with? It depends. And here is what I want you to take away. For a given data retrieval scenario, one may be able to write query in several different ways, and all of them might be able to give the correct results. In such a case, which of those multiple queries to go with? Unfortunately, here I don't have a one size fits all type of advice. The best choice depends on factors like performance, readability, maintainability, and of course, personal preference. So I would write a query in an approach that I think would be the best approach. And depending on how it performs, I would explore other ways of writing the query. That is our first key insight. Let us move on to the next one. It is something you may come across once in a while. In most table joins, a column in one table maps directly to an equivalent column in the other table. However, there are cases where you need to match records based on a range rather than an exact value. In such cases, a value from one table is compared against a lower and upper bound defined by two columns in another table. This type of setup is commonly referred to as joining tables on a range of values. To demonstrate it, the example we have got here is that we have invoice table and invoice category table. Now, for this example data, the task on hand is to write a query to extract data from invoice table along with invoice category that each invoice falls into. For example, for the invoice ending in 2001, the invoice amount is $7,500. For this invoice amount, we want to find out what the invoice category is. In this example, for this invoice amount of $7,500, it falls under the invoice category of $5,000 to $10,000. Excuse me. And like that, we want to write a query to determine the invoice category for all the invoices. So let us switch over to the notebook to see the query in action. I think this will be a quick one. So let us go straight into it. Here, as you can see, we are joining the invoice data frame with invoice categories. And while doing so, the join condition that we are specifying here is such that from the invoice table, we are taking the invoice amount column and joining it with the range of values in the invoice category table. So while doing so, we are invoking the between method of the column, and to that between method, we are passing the boundaries for the range of values. And in this case, our lower boundary, the first one is lower boundary from the invoice category table, and the second parameter is the upper boundary from the same invoice category table. So that way, here we are joining the one column from left table with the range of values from the right table using the between method of the column. So that is about joining the columns on a range of values. Finally, let us wrap up with the last of the scenarios in practical insights section. Role-playing dimension is another classic scenario that you will come across in a data warehouse. But what is a role-playing dimension? To answer that, say we have a fact sales table in a data warehouse. Fact sales table. It stores sale transaction records. A sale transaction record may have order date, ship date, and delivery date, and so on. In a normalized data model, instead of directly storing these different dates in the fact table itself, the foreign keys for the same are stored in this fact table, and all those dates would be pointing to the dim table. In this case, it will be pointing to the dim date table. But the thing is, the dim date table is physically just one dimension table. That is, in the database, you would just see one physical table for dim date dimension. In other words, one physical dimension table is playing the role of multiple logical dimensions. Order date dimension, ship date dimension, and delivery date dimension, etc. For this reason, such dimension tables are called as role-playing dimensions. The scenario here is that we want to retrieve transaction details from fact sales table along with order date details, ship date details, and delivery date details. One thing to note here is that a given date may have details such as the full date itself, along with which quarter the date falls into, and is the date a public holiday or not, and which fiscal period the date falls into, etc. Now, coming back to writing the query itself, given that we have three different dates to get the details for, how to join fact table to one physical table to get the three different details. Let us see the next. The question was how to join a fact table to one physical dimension to get the details for three different dates. The thing is, we cannot directly join a fact table to one physical dimension multiple times in the same query. Instead, we will have to alias the dimension, and in our case, we have to alias it three times. Here we have the dim date dimension, and we want to alias it, or we alias it three times. Once to represent the order date details, and then another second alias to represent the shipping date details, and third alias to represent the delivery date details. Once you alias the physical dimension, one physical dimension into multiple alias tables as many times as required, use those alias tables to join with the fact table. It is that simple, isn't it? Now let us step into the notebook and look at the implementation. Hoping our conceptual understanding of role-playing dimensions is clear, understanding the code is no-brainer. In the code here, we have the fact sales data frame, and then we are aliasing the dim date data frame three times. Once to represent the order date, and second one to represent the shipping date, and third one to represent the delivery date. Once we have those four data frames in place there, then joining them, here we are joining the fact sales data frame with first with the order date alias to get the order date details. Similarly, joining with the ship date alias and delivery date alias to get the details for the same. Once we join the fact table data frame with those three aliases, retrieving the details for order date, shipping date, and delivery date is pretty straightforward. And that's all to it for the role-playing dimension. The key thing here is to have a clear conceptual understanding of role-playing dimensions. Once you have that clear understanding, clear conceptual understanding, writing the code for the same is no-brainer. So overall, the key takeaway from this example is we come across role-playing dimensions very often in a data warehouse scenario. Date dimension being a classic example of it. When the same physical dimension is playing multiple roles, all we have to do is alias that physical dimension as many times as the number of roles that that dimension is playing. Once aliased, the joins between them is no different to joining multiple tables. And that brings us to the end of the series, Write PySpark Joins like a pro. Over the three parts, we have gone from understanding join types to writing join conditions for different scenarios to finally exploring common pitfalls and practical insights that can help us join data frames like a pro. My hope is that this series has given you both knowledge and confidence to handle joins efficiently in your own PySpark projects. Maybe even a desire to experiment with different approaches on your own. Remember, writing joins is tricky, but having a clear understanding and with some practical tips, we can avoid common mistakes and write clear, readable, and performant joins. If you have enjoyed the series, don't forget to like, comment, and subscribe so that I know what kind of content to create next. And if you have any questions, drop them in the comments. I would like to hear about them. Thank you for following the series and happy PySparking.